right, so we are now looking at this question here, and it says a light elastic string has natural length A and modulus of elasticity 24 mg. One end of the string is attached to a fixed point A. The other end of the string is attached to a particle of mass 2m. So in part A, find in terms of A, the extension of the string when the particle hangs freely in equilibrium below A. All right. So here we've been given that the natural length L is equal to A. The modulus of elasticity is 24 mg. We've also been told that the particle is hanging freely, okay, from a point A. So let's say the particle is here and is hanging freely. The natural length is A, and the weight of the particle, since we've been told that the mass is actually 2m, okay, so the weight will be 2mg. All right, so we also have tension, and here we are at equilibrium. So at equilibrium, we know that T is equal to 2mg. All right, T is equal to 2mg because the forces here are balanced. All right, and we also know that T is equal to lambda x over L. So therefore, we can say that 2mg, which is T, is equal to lambda, which is 24 mg of the extension x, and that's going to be over A, which is the natural length here. All right, so to get the value of x, we're going to say that it's equal to 2mg times A, and that's over 24 mg. And here, mg goes into mg once, and 2 into 24 12 times. So the answer here comes out as A over 12. So that's the answer. All right, now we go on to part B. On part B, they say the particle is released from rest. Find in terms of A the distance of the particle below A when it first comes to instantaneous rest. Okay, so remember A is the point from which the particle is projected. That's the point A. So it is projected from A, and it is going to go, okay, it is going to go downwards until it comes to an instantaneous rest. All right. So the question says we should find the distance, the particle of the particle below A when it first comes to an instantaneous rest. But remember, it was also released from rest at A. All right. All right. So the natural length is still A, and we're going to take this level to be h equals to 0. All right. The level where it comes to an instantaneous rest. So that is where the speed of the particle will have become 0. So the distance of the particle below A is this distance. That's actually what we are calculating. This distance, which I'm going to call D. So that's the distance we are actually looking for. So it starts with an initial speed of 0 because it has been projected from rest and goes all the way down until it comes to an instantaneous rest where V is equal to 0. So the total initial energy is equal to final or total final energy, right? So total final energy. All right. So that's what we're going to use. All right. Now here we are saying that the initial kinetic energy should be 0 because the initial speed is 0. So we're going to have 0 for that. As for the gravitational potential energy, we're going to say the mass, that's 2m times g, times the height or distance from h equal to 0. And that distance is actually d. So 2 mgd is the gravitational potential energy. Then when it comes to the elastic potential energy, that's going to be 0 as well because at A, there is no extension. Extension is 0. So we're just going to work with this. So this is going to be equal to, for the final, okay, because this is initial. For final down here, kinetic energy is going to be 0 since the speed is 0. Then the final gravitational potential energy is going to be 0 as well since h is 0. Then the final elastic potential energy is going to be, remember, elastic potential energy is calculated lambda x squared over 2L, right? So basically that's going to be lambda, we had gotten that to be 24 mg. So we have 24 mg times the extension squared. The extension in this case will be this. That's the extension, which is d minus a, so squared. And that's divided by 2 times the natural length, so that's 2a. All right. So that's what we have. We're going to divide both sides by mg, all right, and multiply both sides by 2a. So on the left side, you'll be having 4 AD, and that's equal to 24 of D minus A squared. From here, we can divide both sides by 4, can't we? Yes, we can. And we'll be having AD being equal to 6 off. And now we can expand the bracket. That's D squared minus 2AD plus A squared. Okay. So AD is equal to 6D squared minus 12AD plus 6A squared. All right. And rearranging this, we'll be having 6A squared, and that's going to be minus 13AD, and that's plus 6D squared equal to 0. And we are going to factorize, which will give us, if we factorize this, we should have 2a minus 3d of 3a minus 2d. Okay, so let me write that properly. So I said here 3a minus 2d. So the possible values of d we will get then should be 2a over 3 or 3a over 2. Okay. So this is what we are having here. All right. Now we are going to reject this particular value because D has to be greater than the natural length. Okay. So therefore, D has to have the value 3a over 2. So this is the solution here. Okay, I don't know if you got that. Did you?
Yes, sir. I just like when I was doing this question,
Yes.
how because the initially U is equal to 0, right?
Yes.
They also said the particle is released from rest.
Yeah.
So you can say kinetic energy is equal to 0, and elastic potential energy will also be equal to 0.
Yes.
But the when I was calculating gravitational energy,
Yes.
I thought, in the if you go over part A, they say the particle has reached the equilibrium position, right?
Yeah.
Which means it's not moving, like D equal to 0. So I thought you just had A plus the A over 12, or use A over 12 as the height for gravitational potential energy.
Okay.
And
So
then I add it back or something.
all right. You needed to understand that A and B are two different situations. On A, it was a situation where the particle was hanging freely in equilibrium below A. All right. So this is a situation on its own. But for B,
Oh,
B is a totally different thing because we are having the particle being released from rest at A. All right. So you needed to consider that the fact that B was a totally different situation altogether.
that'd be fair.
All right, that's fine.